Okay, I think I've worked it out. This Desmos version is just dedicated to this fraction. So just running through this again, there's only 3 base units, the Lorentz transform there, and then Einstein said therefore time dilation is the inverse of epsilon, which is L, but I have decided that it's T. It's actually distance over velocity, which is just the usual velocity is distance over time, so I've just done that. So it's not time, that's time. Okay, now there's the relativistic slide rule, but I'll just leave it out for a second. And it's passing through water at the moment. Okay, so B is therefore 0.6, meaning that the refractive index is 1.333 recurring. So if you look at that, that's 1.333 recurring, so that's T. Now let's say that this is the surface of the material here, and we're 3 layers down, but these are tiny, these layers, and the black lines are the normal to the surface. So this is the surface of the material, this is the normal to the surface, this is the angle of, this is the ray coming in, the incident ray, and then it's either transmitted into the material or it's reflected off the surface back out. And the relativistic slide rule is always Brewster's angle, therefore the angle between the transmitted and the reflected ray is always 90 degrees. Okay. Now there might be other rays coming in, like that. And let's say the material is glass. You can see that, see how it changes. The higher the refractive index, you can see the material, the distance is decreasing like that. Okay, so let's go back to just passing through the vacuum itself, where the angle of incidence is the same as the angle of transmission, so that's just going through the vacuum, in other words. Okay, let's go back to this one so that we can differentiate. Now let's put the relativistic slide rule in. There it is, and let's take those lines out. And interestingly, that distance from there is 0.5. So I'm going to say, I'm going to put the circles in. I think of the circles as an integration of all the differentials. So there's the circle for the boson, there's the circle for the fermions, circles for the fermions. So these are the shells, I think they're called shells in electrodynamics. So notice that this is the point particle. The point particle is It's right there. That's the point particle. Okay, and it's always on the shell. Just goes around the shell. Yeah. And this is a vector of magnitude half. So that's the vector for the spin half particle from there to there. This is the vector for the boson. Goes from there to there. That's always 1. So that's a spin 1 particle. Now, notice that if you go from there to there, the half particle doesn't go as far, so you've got to rotate this one 360 degrees around that, and then around that till it gets to the bottom. But at that point, this vector is simply gone 180 degrees, so half as far round. So you have to do a full 720 degrees to get this spin half particle to come back up to the top. In fact, I'll just leave all of this out, and I just say that the boson vector, the spin 1 particle, is subject to length contraction, whereas the spin half particle is not, and therefore you have to half the angle to get the probability of collapse, which is this distance from there to there, the probability of collapse. So for a velocity of 0.6, the probability of collapse is 0.64, or 64% probability of collapse, and it increases to 100% probability of collapse there, and the spin half particle rotates around 180 degrees and 0 probability of collapse there. So you've got to go well, you've got to go around that one 360 degrees, but you have to go around both, so the boson does, spin 1 particle has to go around both, so it's actually 720 degrees. Anyway, that's my understanding at the moment, but I thought it was pretty amazing that I mean, I can see why, but now I've got my spin half vector, I've got a reason for why its base is always attached there, because before I couldn't think of a reason, but now I can see that incident ray always goes through there, and that's because of Brewster's angle, which is actually the cause of this right angle, is this right angle. I mean the Lorentz transform, where B is at right angles to L, and so this ray is actually going from orthogonal one direction, orthogonal direction to another, and so that's why it's always staying in that half. It's always going through that half, because it's the angle is one angle, as the angle of incidence is say increasing, the angle of transmission is decreasing, and this is because the fractive index is increasing.